Hi y'all, welcome back. Hi, and we're going to continue our 2021 AMC 10A debrief. What is the volume of the tetrahedron ABCD? And then it proceeds to list some edge lengths. So let's take a look at what a tetrahedron is first. And it is a 3D shape where we've got four sides that are all triangles, and I hope that sort of looks like one. So we have a base triangle, and then we have three triangles that meet at a vertex. So I can call this A, B, C, D, or maybe I'll draw it out more like that. Something like that. So it's a pyramid, except with a triangle at the base. And so what I noticed right off the bat is that I'm seeing that AC is 3, AD is 4, and CD is 5. And so I noticed that there's a triple 3, 4, 5. I'm working with a lot of triangles here, so that makes me think, hey, Pythagorean theorem. So what I want to do is I want to test out combinations of side lengths. I want to see how this tetrahedron would look when I break it up into all the separate triangles, because knowing things like the Pythagorean theorem could really come in handy over here. So I've got a triangle ABC. I've got a triangle ADC. I've got a triangle DBC, and then I've got a triangle ADB. So if I use these side lengths, I'm just going to go through and fill out all the side lengths here real quick. So I've gone through and filled out all the side lengths, and now I can start looking for patterns. So I already know this is a Pythagorean triple, and I can just compare the rest. So I can say 2 squared plus 3 squared equals 13. Oh, hey, that adds up if I take the square root of all that. Get root 13, and that's the side. So here, this is also right triangle. 2 root 5 squared plus 5 squared is going to give me 20 plus 5, which is 25. And the square root of that is not equal to root 13. All right. 4 is bigger than the other two, so I'm going to do 2 root 5 squared plus 2 squared. And the square root of that is going to be square root 24, which is not equal to 4. Okay, so I've seen that I have 2 right triangles in here, and that actually simplifies our calculations a lot. And that's because if the base, and any of these can be the base, recall. So if the base is a right triangle, what that means is I've got a base like this, and I can just duplicate my tetrahedron so that they fit together and the base becomes a rectangle. And now what it is a pyramid. Now, if I divide the volume of that pyramid, and now they'll meet at some vertex over here. If I divide the volume of the pyramid by 2, then I get the volume of this specific tetrahedron. So the volume of a pyramid is nothing but the length, width, so here is the base area, times the height, times 1/3. And now I'm going to multiply that by 1/2 because I know that I only want the part of the tetrahedron that fits like that, and not the other half that I added in to make it a pyramid, to make computing the volume easier. So I've got 1/6 and the base length, width, and height. So if I take the length times the width times the height, so I'm going to say this is the height is going to be maybe AB, and then my one side is going to be AC and the other side is going to be AD. So I'm just going to make it all just connect to A. So I've got 2 times 3 times 4 divided by 6, 2 times 3. That cancels out. My answer is 4, which is option C. And the reason that I chose to use AB, AC, and AD as my length, width, and height for this. I should have specified it earlier, but it's because the right triangles I found are relative to point A over here. So I've got ABC, that has a right angle over here. Let me make it a little bit more clear. ABC has a right angle over here. And ADC also has a right angle over here. So I'm choosing these sides that are relative to point A that contribute toward that right angle. And so there's your answer. It's option C.